So we want the integral of the vector field x2 along a path, which is an arc from -1, 0, or sorry, from 1, 0 to -1, 0. Okay, what does that look like? So we'll make an arc of a circle. Something like this. Traveling in this direction. Yep, question?
Or I just wanted to make sure, like for the when you were doing the computing the integrals on the upper board.
Sure.
The second one, is it supposed to be dy over dt times
yes,
dy, or is it supposed to be dt?
Should be dt. Thank you. Yeah. Yes, thank you for catching that. These guys are sort of morally supposed to cancel out. Yes. Yes, good catch. Okay, so we've got this vector field that's kind of always pointing upwards. The farther we go out, the more tilted it becomes. But we've got some vector field pointing along this curve. And we want to calculate the path integral. Okay, so set up the integral. Oh, first we need to get a parameterization of the path. Okay, so path. Right, we want a path that starts off here, comes around, makes us think of an arc of a circle. We've got a parameterization for the circle. This. Okay, now we've got our vector field, we've got our path. The bounds here would be t goes from 0 to pi. Okay, and then our r prime is the derivative of this guy. Okay, and now we've got a non-constant vector field, right? Now our vector field depends on our inputs a little bit, so we'll input this into our vector field. Here. We dot them together. And now we've got a one variable integral that we can, in principle, handle. Right, we've got this product of things and a cos, but it's a one variable thing that we can do. Okay, so the first step with these is to notice that you've got a sine and a cos. So that reduces to minus half 2t. So just the trig identity that happened there is following.
Wouldn't it be easier to solve this by substitution?
Yeah, there's a nice substitution you can do here.
Substitute the sine and then the cos ddt will go away.
Yeah, that's a nice way to do things as well. I'll just keep going with this one, but yes, you can alternatively do it by substitution. Okay, so we get negative quarter cos 2t. We get okay, so these folks go away and we're left with actually this all go away, we should be left with negative a quarter. Yes?
What are the first two?
Right, so, oh wait, cos of, oh right, yeah, sorry. Yeah, so we should have 0 and 2 pi here, yeah? So we should get 1 there. Yes. So this term stays now, and we get 0. Okay, nice. Sweet. Yes.
In the first line was negative a half sine 2t,
Yeah.
and then it comes down and it's positive a quarter.
Aha, right. Right, so the deal there is we've got the integral of this guy. We want something whose derivative is negative sine 2t, right? So we want a half here, and we want a positive thing. Yep.
You drew the vectors over there as like they're straight up in the middle and they point you down as you go to the right. And this represents the sum of those vectors over that curve.
Sorry, say the first part again?
What does this integral represent in terms of the vectors?
Right, so it's how correlated is, how correlated is this red path with these blue vectors? So I guess sort of what's kind of morally going on here, like one kind of intuitive way to see that this should zero out is that these blue vectors are symmetric with respect to the path. Right? So all the positive contributions will cancel out all the negative contributions.
So even if you had from like negative infinity to infinity, anything that's centered around 0.
And is symmetric.
The vectors are gonna cancel out.
Yeah, so if you had a parabolic arch, with this setup, it would also zero out. Or if you had a big, long, snaky path, that as long as it was symmetric with respect to the y-axis, it would zero out.
And then if you just, instead of starting from the left side of it, if you started in the middle and then only went to the right, you get some positive number.
Yeah. If you started here and only went to the right, you'd get probably a quarter.
Does the direction of the path matter in general?
Yes. Yeah. And it matters up to a negative sign. So if you Right, so if you switch the direction of the path, you get something like this. Okay, so it's a little bit of practice with line integrals. Yep. Question there, Emily?
Yeah, I'm just curious about, so the blue on the little graph thing
Yeah.
is the field
Uh-huh.
vectors, right? Is that, and that's x2? I'm
Yes.
just wondering, wouldn't, so x is like kind of depends on where they start on the x line, but wouldn't it always be kind of straight because you're going to 2, or like how did, like,
Right, so yes, so
I'm
I've
just
tried to
like,
draw it.
visualize it.
Totally, this is great. I've tried to draw it so that the heights are all 2. So I've tried to draw it so that the heights are constant.
But why aren't they like straight if that's the case?
Because they've got this component here. So let's just take a moment and draw a couple of these vectors very accurately. Okay, so if we start off at 1, 0, then our vector is going to look like 1, 2. And if we start off at 2, 0, then we're going to get a little bit more sloped. Okay, so they all have the same height. They're all of height 2, but the
Oh, I see.
x component is changing from one vector to the next.
It's the, okay, it's the slope that's, that it determines.
Yeah, the slope is, the slope depends on the base point.
Cause I was
Why-
thinking like, that's not 1, 2, that like, then you
Aha.
have to think that that's 0. You know, if you have to go from that, okay, I get it.
Cool, sweet, yes. Okay, so we'll